So, very happy to be here and to see that you are so numerous. I didn't expect it to have such a full room, but nevertheless, I decided to start a little bit from the basics, since the title of the lecture I've been given is Introduction to Cosmology. So I hope it will be not too much repetition today for people who have already had a course in GR on cosmology, but just to setting the stage, today will be practically the basic stuff of cosmology. Then tomorrow we will, so the plan of the lectures is the following. So we have So today we will have the introduction. With a bit of general relativity and cosmology. Tomorrow we will go on with, again, the part of the, if you want, more classic side of cosmology, which is practically inflation. And the cosmological perturbation. And then on the third lecture we will go to the thermal universe, and there we will discuss a bit Big Bang nucleosynthesis, and we will discuss also dark matter. At least the start. And then in the last lecture on Thursday we will continue on the thermal universe, again a bit on other candidates of dark matter, and if we get there, some elements of baryogenesis. But I think you have also lectures on it in last week, if I remember correctly. So I will not really go to the detail. I will try just to get there so that you can get the connection later on. Okay, so this one is the plan. Of course, it's a bit optimistic, especially because it's done on the blackboard. Usually the rhythm of the blackboard is a bit slower, so I'm not sure I will be able to cover all. In the case also, it's probably not important that I cover all. It's more important that you understand what I cover. And so you are welcome to ask questions at any moment, and we can stop any moment to check if you didn't really understand things, so that we have at least a good foundation for the rest of the school. Okay, so introduction to GR. The first element we have a little bit to cover is the general relativity. So of course this should be clear that this was the beginning of cosmology. Before Einstein, before the writing down general relativity, nobody really knew how to describe the evolution of the universe. Okay, the idea before was that the space was actually static. It was kind of absolute space, and time was a variable which was completely independent, and it was just a kind of sequential quantity which was more or less taking care of the evolution of the system. It was only with Einstein, first with the special relativity, where people he realized that space and time are actually together, and indeed the time is not the same for all observer, and you have to do as usual. Well, the transformation were of course known also before, how to change the coordinate system. And then later what he also realized was that the curvature and the geometry of space-time is also a dynamical variable in that sense. And this led to general relativity. But one important principle we also have in this respect in cosmology, and which also was introduced by Einstein, was the cosmological principle. And not only him actually, but the cosmological principle is also a needed ingredient, because without this it would be too complicated practically to describe the universe. What does the cosmological principle say? The cosmological principle states that the universe is homogeneous and isotropic on large scales. Well, I hope you know all homogeneous and isotropic. Homogeneous, of course, means that every point is more or less the same as every other, and isotropic, that in every direction you look, you see the same universe. And of course, the other important thing is on large scale. What does it mean on large scale? Well, it should be clear that in this room the universe is not homogeneous isotropic. In the solar system the universe is not homogeneous isotropic because you have a planet or you have a void, then you have the sun, etc. You need to go at a sufficiently large scale. And the sufficiently large scale, if you want to have something in mind, is more or less the scale of the horizon now, or the scale of these sizes that you can observe on the CMB. For example, the CMB it's practically one of the largest scale we can observe. Then of course also you have all the observations that comes from a large scale structure, which we will discuss briefly later on when we look at structure formation. And in that case as well, you see that if you look, for example, at the density contrast, this is usually the quantity which is of interest, is the density at the place x minus the average density divided the average density. And this quantity is usually nowadays of order 1. For example, on the solar system, in the everywhere where there is a structure already formed. But if you go to large scale, this quantity becomes a quantity smaller than 1. So you have, as I said, if you go to scales which are on the order of 1000 megaparsec or so, you start to see that this quantity delta is actually a small quantity of the order of 10 to the minus 3, and in the CMB, for example, this is also corresponding to the temperature fluctuation, which is of the order of 10 to the minus 4, 10 to the minus 5. Okay, so, and this is exactly the reason why we can take at a first order approximation isotropic and homogeneous universe, and then on top of it, and this is something we will see tomorrow if I'm not able to introduce it today, we can do the perturbations. So we will use the fact that delta is small to write, for example, something like an homogeneous universe plus fluctuations. Okay, so if you want background at leading order, has delta equal to 0. Okay, and this is what I will discuss now. So how can we discuss isotropic and homogeneous universe? In order to describe a universe, we need, as usual in GR, a metric. So this is the famous Lemaitre, Freedman, Robinson-Walker metric. And this is exactly the metric which satisfies exactly the homogeneity and the isotropy. And it is practically the simplest metric you can write down for a kind of homogeneous manifold with a spherical symmetry. So you have in the first part is the time, which is the usual dt square. So this is the same as in the Minkowski metric. But then you have a scale factor, which do depend only on time. And then you have the three-dimensional metric, which generically it can be flat or curved. And generically the expression can be written in this form with a radial coordinate, with a factor which depends on a k parameter. And then you have the usual spherical angular part with an r square. So the omega is, as usual, in 3 dimension, is the theta square plus sine square theta d square phi. Okay? So you see that immediately that here you have a really very simple expression. So you have only one dynamical variable, which is A. And we have one parameter, which is K, which I can probably write also in a different color. And the rest is practically just the usual coordinate, like in the Minkowski case. Notice, of course, I take the signature 1 minus minus 1 minus 1, so as usual. So you can compare it to the Minkowski metric. And in Minkowski, you have a ds square is equal dt square minus you could have again dr square plus r square d omega if you have spherical coordinates. Well, I actually don't need, I think, the omega square. It's usually just the omega. Okay, so what does it mean for the metric? Of course, you know all that I can define, of course, a tensor, metric tensor, g mu nu, which multiply the elementary distance, dx mu and dx nu. And therefore, if you look at the metric above, you see immediately, of course, in this case, it would be just 1 minus 1 minus 1 minus 1. In this case, instead, the metric is again diagonal, and you have again a 1. But here, of course, you get a minus a squared t, 1 minus k r square. And on these sides, you get also a minus a squared t r square. Sorry, I forgot the r square, of course. And minus a squared t r square sin square theta.
In the second column, there is no r square, no?
Sorry, in the second column?
There shouldn't be an r square.
Sorry, there is no r square. Yes, you're right. Here there is no r square. Yeah. Okay, so you see immediately the advantage we have. Generically a metric, we'll see it also later on. It's a symmetric 4x4 tensor. Symmetric 4x4 tensor has exactly 10 independent quantities. So you see it immediately. You have 4 in the diagonal, 3 in the next 2, and 1. If you sum up the number from 1 to 4, you get exactly 10. So usually, if you would just write down the most generic metric, you would have 10 degrees of freedom. For the Freedman-Overson-Walker metric, we have only 1 degree of freedom, which is the scale factor, a square. And all the rest is practically fixed by the geometry. So this is the big advantage of this metric. Now we have to get a little bit what is the physical meaning of this parameter k. To get what is the physical meaning of k, we have just to compute what is the curvature in 3 dimensions. So to do that, we just need to compute the, let me turn. Yep. Is it? Okay, so let's say what is the meaning of k? As I said, I can compute the 3-dimensional curvature, which is nothing else as the Ricci scalar in 3 dimensions. I write it like this, and if I do that, I obtain something of this form. K r squared. No, sorry, that's wrong. Too many factors. It's a squared t. So you see immediately that k squared determines the curvature, in the sense that k, of course, the sign of k can be positive or negative. If it is positive, you have a positive curvature. Negative, you have a negative curvature. K equal to 0 will be automatically 0 curvature. Yes?
Excuse me, on the left-hand side you have 3R.
3R is because it's the three-dimensional curvature. The if you want the Ricci scalar in 3 dimensions, we will later on have the Ricci scalar in 4 dimensions, which will have other contributions. So this will not be actually connected to the 3-dimensional curvature, but to the 4-dimensional curvature. Now, in here you observe already also.
So-called extrinsic curvature.
Yes. And when you have here, you also observe that this depends on the scale factor A. So you see immediately also that how exactly the curvature is depends on A squared. And the real value of k actually can be rescaled into rescaling the scale factor. So what is important is only if k is positive, negative, or 0. That is why usually people use k to define it only either +1, -1, either +1, 0, or -1. And the +1 is, of course, the closed universe positive curvature. So if you want to think about something, you can think about a sphere. K equal to 0 is the flat universe, and k equal to -1 is the open universe or hyperbolic universe. So in that case, the curvature is negative. It means in one direction you have positive curvature, in other direction you have negative curvature. And if you want, usually the way to cope with these different spaces is actually to rewrite the radius here coordinate in a different way. You can redefine a chi variable, which is nothing else as dr squared 1 minus k r squared, and solve this equation. And then you see immediately that chi of r has 3 different solutions. You can have an arcsine solution of r for k equal to 1. You can have just a solution r where k is equal to 0. And if you are in the same case of k equal to -1, you get the arcsine hyperbolicus. And in this way, you are practically able, if you go to the variable chi instead of the variable r, you can treat all the 3 different spaces in the same way, just using d chi square instead of r. And you substitute the solution depending on the value of k. Now, in the future, I will actually concentrate on the k equal to 0 case. And this is not by chance, it's because this is what seems to be what we measure. Okay, if we measure now the 3-dimensional curvature, this is practically very near to 0. Of course, as you see immediately here, this doesn't mean that it is exactly 0. It could also mean that indeed it is also so that the universe is very large. So a square is large, and this means this would actually reduce the curvature. So we do not really know if the universe is exactly flat, but it looks very much near to flat, and therefore I will concentrate later on to the solution with k equal to 0. Okay. So I have now just another important redefinition to introduce. Because we see immediately this metric actually doesn't look very different from the Minkowski metric. We see that the part here, if we could be able to take out an a square from everything, then it would look like more or less like a rescaling of the Minkowski metric. And indeed, this is exactly what you can do if you redefine the time. You redefine to be the conformal time, which is defined with an additional factor of a square. So this is usually useful in cosmology to define the conformal time. Whoop. The conformal time is, I will use eta, is a of eta d eta. Okay, so I scale the time in such a way that I have an additional factor of the scale factor. And then it should be clear that therefore then I have the simple metric where the a square comes in front of it. No R square here. Okay, so this part is nothing else as the Minkowski metric for the conformal time, though. Okay, and this scale factor is just a conformal factor because you can rescale it, a conformal transformation of the metric or a scaling transformation of all the coordinates that is exactly equivalent by multiplying by the scale factor. And this way of writing the metric has, of course, the advantage that we can see immediately that we can immediately read out what is the light cone in cosmology. Yes?
In order that to be Minkowski, instead of R, you should use chi, no?
Yes, yes, sorry, you're right. It's in chi, yes, you are correct. I was thinking again at the case k equal to 1, where it doesn't matter. But yes, you're right. So, okay, let's write here in k, and then everything is indeed Minkowski. Yes, that's the more correct statement. Yes, as I said, if you concentrate in k equal to 1, chi is equal to r, so it's exactly the same. But if you want to be in the generic case, you need to also use the chi variable. And this allows me immediately to see what is the light cone, also in cosmology, because we have usually the light cone means ds square has to be equal to 0. This means that the scale factor here doesn't matter. It's just a factor. It's always different from 0. So I can forget about it. If I want to look at the light cone, especially if the light is moving along a radial direction, I have the following solution. The eta square is equal, or the eta is equal to plus or minus d chi. Okay? So in this coordinate, the light cone is a light cone, as usual. So you have just the usual light cone with the coordinate chi and eta. And and the light moves along the cone, and inside the cone you have the massive particle move within the cone, as usual. So in that sense, there are many of the intuitive arguments you have for Minkowski you can automatically use in the case of cosmology if you use the variable eta and chi. Okay? And we will use it later on also to see one thing. Actually, we can see it immediately. It should be clear, therefore, that yes. Okay. We have, therefore, that since the light trajectory is given by this formula, if you look at light which propagate along the radial direction, the solution of this equation is very simple. You have that the difference in time between the time of emission and the time of observation, for example, this is nothing else as the chi of the observation minus the chi of emission. Okay? Or if you want, here for flat universe you have you can rewrite and go from the eta to the time using this relation. You see a difference in eta is nothing else as the difference in time divided by the scale factor. So you can write at the eta, as long as you are in a relatively small range of eta, as a delta t over a of t. And this one is therefore equal, in case you are flat, this is exactly delta r, because chi is r for flat universe. And this is already telling you that delta eta is actually a constant. If you have, for example, if you look at the delta eta as the interval between two maxima of the wave, of the light wave. So, for example, you can just look at what it is the, consider two maxima of the wave, of the light wave. So we have practically, as usual, we look at a light wave, and we have, of course, the difference here I will consider as a delta eta. And delta eta will remain actually constant, because this is exactly, for a light ray which moves along the radial thing, this is constant. So this is always equal to delta t of emission over a at t emission. But this will also be the same as the observation time. Okay? So in that sense, this delta eta will be equal at emission. So this would be the emission point. And the same at observation. But on the other hand, the time will be different at emission and observation, and also the scale factor. So you see immediately that from this expression, you obtain that the light actually would change the frequency and the wavelength depending on the scale factor. And in practically, you have that the wavelength at observation and emission is equal to the ratio of the scale factors. T emission. Okay? Now, this ratio of the wavelengths is usually also written using the redshift. So it's a factor of how much the wavelength changes. So this is usually also equal to 1 plus what is called z. Z, of course, we know it now, it's a redshift. Of course, in principle, it could also be in a blue shift originally. But since the A is growing with time, the A at observation is larger than the A at emission. And therefore, you have here z is always a positive number. And we have actually a possibility to measure, if you want, the scale factor of the universe by measuring the redshift of light emitted in the universe. So if we look in the past, we will get redder and redder light. And z is usually another variable we can use as a time, if you want, or a kind of clock for the evolution of the universe. So we can use either the normal time, we can use the conformal time, eta. We can use actually the scale factor, because the scale factor, as long as it's always growing, could also be used as a kind of clock. Or we can use the z variable. Okay, and in cosmology, people use all of them, often actually the z, because the z variable is actually the easiest to measure, because you just measure the redshift of light, and you know how far you are in the universe. And you know probably well that you can measure, for example, supernova up to z of 1 or 2. You can measure, of course, this large-scale structure up to z of order 6 or something like that. And then, for example, the CMB comes for a z of the order of 1,000. Okay? So this is a bit the range of z you can get to. And if you want, the important thing is that you can change variables from all of them. And the relation are the following. You have, of course, dz over 1 plus z. This is equal to minus dA over A. and it's equal to minus h of t dt. H of t I have not defined yet, now we will get to that. H of t is the derivative, so it's nothing else as a dot divided by a, and we get to that in a minute. So these are, if you want, the important quantities that are used in cosmology, and if you look at many plots or data, you will often see things plotted at different values of z, and this is nothing else than looking at different epochs in the universe. Okay? Good. Now I think I have to erase, since I used all. Whoop. Okay, so it should be clear that until now we have just played around with the metric. Okay, I didn't do anything else that changing definition, redefining. I just using the metric. But what we want is also to solve the dynamics. Okay, and the dynamics we can solve using the Einstein equation as usual. So well, the other side. Okay, so now of course, as I said, we want to also solve the dynamics. And to solve the dynamics, we just use Einstein's equation. Okay, so I hope you're all familiar with GR. In principle, you can write down the Einstein-Hilbert action, do the variational procedure, and obtain from it the Einstein equation. I'm not going to do it, because otherwise it will be too long. I just give you the equation. You have an equation which relates the Riemann, the Ricci tensor and the Ricci curvature with the energy momentum tensor of the matter. And here you have the usual 8 pi gn t alpha e beta. Notice that I'm using one index up, one index down. It's as usual in GR, it's not the same if you have it up or down. You have always to move it up and down with the metric. And I use it to up and down just because there I have a delta here. Instead, otherwise I would have a eta metric. And it should be clear here, we have the Ricci scalar and the Ricci tensor, which are related to the Riemann tensor, which is related itself by the Christoffel symbols. I can write down all the expressions, I have them here, but I hope I don't have to, because it's only a lot of indices, and in any case probably you will forget it immediately. And I also may not have the ability to write them completely correctly with the indices on the blackboard. Okay? Now, as I said, so if you want, the Ricci tensor and Ricci scalar are related to the Riemann tensor. Here I just want to mention that the Riemann tensor is practically the GR equivalent to the field strength, okay, for a gauge theory, just to have the connection. It is exactly telling you what happens if you go around a square in the space-time. If you have a vector and you move it around a square, the vector would change orientation. So when you go back to the same place, you would have another vector. The vector would have rotated. And this, of course, happens in real space-time. This means that is exactly why you have here 4 indices. 2 indices tell you what is the surface where this square, if you want, is lying to. And the other 2 indices tells you exactly how the vector rotates. Okay? Usually if you go to a gauge theory, you have only 2 Lorentz indices, and this is because in the case of the Riemann tensor, in the field strength, what you have is actually that you have to write these in the rotation, if you want, is internal space. So the vector is not a real vector in the space-time, is a vector, for example, along the SU3 directions of QCD or the SU2 direction in the case of the electroweak theory. Okay? But the concepts are exactly the same, so it's analogous, as I said, to the F mu nu A that you have, for example, in non-abelian gauge theories, where the A tells you exactly that this is written as a matrix in this internal space. And the Riemann tensor, if you want, is exactly the same construction, but for GR. Okay, so that you have a little bit an idea that there is a connection between gravity and the gauge theories. Okay, so if you go through all this computation to compute the Ricci tensor and the Ricci scalar, you find out actually that it's not a very long computation for the case of a Freedman-Robinson-Walker metric. Why? Because of course the only variable is the scale factor, okay? And the only thing you can derive is actually, well, if you are in the flat case, mostly you derive either in time or you can derive on one of the angular variable, but the derivative, for example, in R is also pretty trivial, etc. So you can find a lot of simplifications. And in particular, I can give you the relation. For example, you can compute well, first of all, already the Christoffel symbol simplifies, and then the R, if you compute the Ricci tensor in the 0,0 component, this also has a relatively simple expression. It's -3 h dot plus h square, where h, as I said before, is the derivative of the scale factor divided by the scale factor, and it is practically the basic quantity you can use. And similarly, you can also look at the diagonal spatial part of the Ricci tensor, and that is also simple. It has again a minus, you have again an h dot, you have a 3h square, and then you have again the curvature that we had before, practically. So you have a contribution, of course, from the 3-dimensional curvature, and in case k is equal to 0, of course, this term is exactly vanishing, so I will not keep it longer. But just, well, let me keep it only in one expression. If you look at the Ricci scalar in 4 dimensions, so this one would be the curvature if you want in 4 dimensions, then you obtain the following. It's a minus 6 h dot plus 2h square plus exactly the curvature term we had before for the 3-dimensional curvature. So you see that even if the 3-dimensional curvature is 0, you have a 4-dimensional curvature which is coming from the time derivative of the Hubble parameter and the Hubble parameter. So when we say that the Freedman-Robinson-Walker describe a flat universe, we mean a spatially flat universe, but it's not space-time flat. Okay? And as I said, this full curvature in 4 dimensions, it's a mixture of the spatial curvature plus, if you want, the curvature along the time direction. Okay, so now that we have these, we can look at the diagonal pieces of this equation. And they are relatively simple. As we see, we have only the scale factor, so we have only either the derivative of the second derivative of the scale factor, which is exactly, in some sense, what we need to solve dynamically for the scale factor. Yes, so we get in particular, let me get the 0, 0 component. And the 0, 0 component is, of course, r 0, 0 minus 1/2 r, since the delta would be just 1. And in this case, this is nothing else as 3h square, well, in principle with the curvature if you want. And then, of course, we can look at the II component. And this is nothing as RII minus 1/2 r. And this is actually, again, also relatively simple. We have 2h dot plus 3h square plus a k over I square. Okay. But what is h dot? H dot is the time derivative of a dot over a. So we see that when we derive here, of course, we can derive the a dot. So we get a double dot over a. But then we can derive also the denominator, and we get an a dot square over a square. So we have, if you want, a double dot over a minus h square. So we can, in many cases, well, we can actually combine these two equations to obtain two independent equations. Well, I can turn. So I can, as I said, combine practically, well, I can use directly the 0, 0 component, which has the advantage that you see here there is no second derivative, if you want, of the scale factor, because we have only h square. And therefore we obtain the first equation, which is actually usually called the Freedman equation. And this is nothing else as the following. From this equation, you have h square is equal to a pi gn over 3 t 0, 0. And then I have minus the curvature part. And then, of course, I can use instead a combination of the diagonal pieces here. And as you see here, I can rewrite h dot as a second derivative of a. And I can combine in such a way to get rid of the h square, in this case, using the first equation. And in that sense, then, I obtain an equation for a double dot over a, which is equal to the following. It's 4 pi gn tii minus 1/3 of t0, 0. Okay? So these are the two main equations we need. Notice that in this equation also the k term has gone away, so this depends only on the second derivative of a and the energy momentum tensor. Instead, the Freedman equation contains always the curvature term as well. Now it should be clear that in order to make any other progress, I need to choose something for the energy momentum tensor. Okay? Of course, in principle, I could just compute what is the energy momentum tensor of a scalar field or a gauge field and plug it in here and try to find a solution. Now, this one is not usually what we do in cosmology, because this is usually much more complicated than what we really need, and then also not always homogeneous and isotropic. Okay? So, but what we can do is we can take as an approximation for the energy momentum tensor a perfect fluid. A perfect fluid has the advantage that you can choose it in such a way that you have a diagonal energy momentum tensor which satisfies also the homogeneity and isotropy conditions. And it is a relatively simple expression where we have only two quantity we can, so the perfect fluid approximation we have then that the energy momentum tensor is connected to the density and the pressure. In particular, we have T0, 0 is nothing else as the density of the fluid. And the diagonal components in the spatial components, Tii, are nothing else as the pressure with the minus sign. Minus P. Okay?
There is no sum there, right? In the you are not summing the indexes, no?
No, here I'm not summing. This is just the one index. So E is not summed. So you see immediately that in this way we can directly rewrite the equations as a function of the density and the pressure of the fluid. And that I can do it here directly. So here I get exactly the density, and here I get the pressure. Actually, I can take a minus sign out, and I get P plus 1/3 rho. Okay? Now this is already telling me a lot. First of all, in the first equation we see that h square can have different, well, h square here, it's an equation for h square. Therefore, we see immediately, if the k is 0, there is no problem. H square is always positive, the density is positive, everything is fine. But if we have, for example, here k to be positive, then we see that we will reach at a certain point a value of a square for which this side will become 0. And this is nothing else telling us that in the case of a closed universe, you will have practically a turnover of the velocity. You would have an expansion of the universe, but then you would have a collapse of the universe again. Okay? So this h square, you can think about it to be the velocity square with the expansion of the universe. And the second equation tells me also another thing. The important thing is I have always here a minus sign. So if I have a normal fluid has a positive pressure, positive density, This means that the acceleration of the expansion of the universe is always negative. This means the universe is always decelerating for every normal type of fluid. Okay? Of course, we know also now that it's not like that, so we need to find some other type of fluid which can change this behavior. And in particular, we see here this factor p plus 1/3 rho. We need it to change a sign if we want the universe to accelerate. And this we will see later on. This is what happens, for example, in inflation. In that case, though, you have to find a particular relation between p and rho in order to have practically acceleration, so a positive value here. So this factor has to become negative. So if you want, as long as p is larger than minus 1/3, so okay, we can write it. I could have turned. Okay, I erased it now. It's the same. So you see it from this equation, as I said, for p plus 1/3 of rho positive, you have a decelerated universe. Okay? And for acceleration, we need we need 1 plus 1/3, or if you want, we can write it in the other way. So p over rho plus 1/3 to be less than 0. And this means nothing else as p over rho has to be less than minus 1/3. But p over rho is nothing else as the equation of state for a fluid. I mean, for a fluid, often you can assume that there is a constant relation between the pressure and the density. This is, for example, what happens for radiation. For radiation, the pressure is 1/3 of the energy density. For the case of matter, actually the pressure is even 0. So you have 0 as a relation. But in both those cases, the pressure would be positive or 0. So you are not in the correct regime. And later on we'll see one simple way to get an acceleration is, of course, is p over rho is equal to minus 1. And we will discuss tomorrow how to realize that through a scalar field. So generically, though, we have these two equations that we want to solve. But of course, we also have a third equation. So which equation do we also have? Yes?
Energy conservation.
Exactly, energy momentum tensor conservation. So the energy momentum tensor is conserved. This means this gives us a third equation. And the issue is it another independent equation or not? It is not, actually. It is an equation which is not independent on these two. You can show that GR is such that in some sense, if you have to have conservation of the energy momentum tensor, also from the other side of the equation. So, but if you write the conservation of the T mu nu tensor, in the case of the perfect fluid, this gives you nothing else as the continuity equation. So you have a d rho in dt plus 3h rho, what was it? Yep. Yes, rho plus p is equal to 0. Okay? So this is nothing else as the continuity equation in an expanding universe. So you have the Hubble parameter. This comes from, again, as usual, the fact you need to use here the covariant derivative, not the usual derivative, of course. And as you see immediately also here, you have a rho plus p. So this one is again depending on how the pressure depends on the density, how exactly the density decreases, for example, where you have an expansion. It should be clear, this 3h is a dot over a. So you see immediately that this is also a time derivative. So if p is equal to 0, you have a very simple solution. Okay? So if you have p equal to 0, then you have d rho in dt is equal to 1 over rho is equal to minus 3 a dot over a. And this means that this is a logarithmic derivative. Here we have a kind of logarithmic derivative again. This means that the only difference is that we have a factor of minus 3 in front of the a. So this gives you immediately the solution rho goes like 1 over a cubed. Okay? Now this one I should have known already in some sense, because this is what naturally you would expect. Since the volume grows, because the radius grows like a, the volume, so the three-dimensional volume grows like a cubed. So sorry, decreases like 1 over a cubed. And the density therefore will decrease like 1 over a cubed. Sorry, the volume increases like a cubed, and therefore the density decreases like 1 over a cubed. Of course, generically the p will also not vanish, and therefore in that case again, depending on the let me check. Yeah, depending on the equation of state, you will get a different behavior of the density. So you generically you can write the equation of state as p over rho is equal to a kind of w constant. Now it doesn't have to be constant always. We will see indeed tomorrow a case for the scalar field where w will not be constant. But let me assume that it's constant. It is constant for the case of a radiation. So for example, photon field, massless photon, or for the case of a non-relativistic massive particle. This is, in this case, the pressure is exactly 0. So it's also constant. But generically, we will see tomorrow a case where this is not a constant. But as long as you take it constant, then it should be clear this equation changes just in this form. So the only change is that the exponent here, it will not be 3, but will be 3 times 1 plus w. So their solution is pretty simple. Rho of a, if you want, would be proportional 1 over a 3 1 plus w. So you see immediately the two usual cases. If w is equal to 0, you have 1 over a cubed. We have already seen it. In the case we have radiation like photons. For the case of the photon, we have 1/3 pressure with respect to the density. And so you see that the dependence of the density is 1 over a cubed. If you want, you can think about this also from the fact that here this is an energy density, it's not a particle density, it's an energy density. This means you have a 1 over a cubed dilution of the number of particles, and you have a 1 over a dilution of the energy of the photon, just because the photon redshifts. Okay? And so that's why you would have to expect an 1 over a cubed. 1 over a fourth. Now, as I said, this equation, as you see, is much easier to solve as long as you have a constant w than the other two. So usually it is actually traditional to take this equation, so the continuity equation, and the Freedman equation as the main equation you want to solve. Okay? And this already tells you practically what is the evolution of the universe, because here, for example, especially in k is equal to 0, you can write directly what is the behavior of the Hubble parameter h square as a function of the densities. So solve the two equations. So you get a Freedman equation plus the continuity. And what you obtain is, as I said, the h square for k equal to 0. So I will drop the curvature. You have that this is exactly as written there, 8 pi gn divided by 3. And then you have the sum over all densities. Okay? Now, the sum over all densities will have different behavior with respect to the scale factor. So here, for example, you would have a density of matter at a reference time times a to the minus 3, for example. Then you would have a density of radiation at some reference time times a to the minus 4, etc. Okay? And then what really determines h square, of course, h square is a dot over a. So you have a first order differential equation that you can solve as a function of the scale factor. Usually, though, you can solve it even more easily because you can often, in some sense, take only the dominant component in the energy density. So I can, let me see, I think behind this one, I think is still one board. Clean. Yes. So you see that due to this different dependence on the scale factor, in different epochs of the universe, we have a different dominant energy density. Okay? So if you look at it in the logarithmic scale, let's say so we have in practice that radiation goes down with the minus 4 index. So this is radiation. Instead, the matter will go down with a minus 3 slope. It means it goes down slower than radiation. This means at the early time, if you start with any density of radiation, the radiation will be the more important, the dominant component. Then we will have a time which is usually defined as a time or scale factor of equality, where the matter and radiation density will be the same. Then I will have the matter which is actually taking over and dominating the evolution of the universe. And then actually what I have even more now is that I have another type of density, which is the dark energy density, which is actually taking over. So the constant, let me write it here. The energy density of a cosmological constant is constant. This corresponds actually to a W, if you want to write it as a perfect fluid, a W of E minus 1. Okay? And in that case, then you have acceleration, of course. And you have a constant energy density. It's a bit anti-intuitive. So the universe is expanding, but the energy density is remaining the same. So you are actually gaining energy, if you want, from the vacuum, in some sense. And this cosmological constant, at a certain point, took over in our universe. At least if it is a cosmological constant, one has to say that usually is not clear yet. Of course, W is very near to 1, the one who has been measured. But it could also be something more dynamical, so a dark energy. But nevertheless, it is at the moment 2/3 of the matter density, so it is the dominant component of our universe. Okay? And this means that you have, as I said, different epochs. So you have originally, in the very early time, you would assume there is a radiation epoch, there is a matter epoch, and now we are in a dark energy epoch. And of course, if you just pick one of these densities here, the equation becomes much simpler, and you can write down actually a solution pretty easily for the scale factor. I'm not going to do it here. In principle, it's a good exercise to do. Since you have a power law for the densities with the different W's, then it should be clear that you can very quickly solve this differential equation and find the behavior of the scale factor as a function of time. Okay, so yeah, generically we have therefore the different behaviors, and if we look back in the universe, we should exactly see these different behavior in the. Also, if we plot, if you want the scale, the Hubble parameter, the evolution of the Hubble parameter with the evolution of the universe. So usually, actually, one important quantity which one uses, which I haven't introduced yet, is omega. Now you see immediately from this equation that you have a particular type of Hubble parameter which correspond to having zero curvature. Okay? And one particular critical density which is exactly defined. So let me write it. Critical density. So given the Hubble parameter, I can compute rho critical to be exactly 3h squared over 8 pi gn. And you see from this equation, if rho would be exactly the rho critical, rho would exactly give you h squared, therefore k has to be equal to 0. So the critical density is exactly equal to k equal to 0 in the equation. Now, since we are in a universe where k seems to be equal to 0, actually this density is one kind of very nice reference density, which we can use for measuring all other densities. Now, this density is not very big. It's actually, the density is more or less something like 10 to the 4 electron volt per centimeter cube, if you put in numbers. So it is, in that sense, it's a pretty low density. Is something like 10 protons in a cubic meter. Okay, so that's the average density of our universe. Okay. And this is usually the reference number which we use for measuring all density in the universe in cosmology. And we define usually, instead of densities, the ratios of densities. So we define this quantity which are called omega I, which you probably saw also in the Planck papers and in other cosmological papers. This is nothing else as any density divided the critical density. Okay? Now, it has the advantage that in some sense it's a number of order 1, especially if the density is relevant today. In particular, you can immediately see that, as I said, the matter density today is approximately 1/3 of the critical density. The dark energy density is 2/3, more or less. Of course, today the radiation, as you see here, it's actually very small. So if you plug in the numbers for radiation, you find that the radiation is of the order of 10 to the minus 4. The density in critical density today. So it's a small number. But this is usually the good quantity to use as a standard reference number in cosmology. It has one slight drawback. What is the slight drawback? Slight drawback, it depends on h, or especially h squared. Okay, the measure of h squared is not so precise. It is getting better, but there are still some discrepancies. You probably also heard, in particular between the CMB measurement and the local measurement of h squared. And this can be a little bit a problem if you want. And what people do usually is to rephrase these in a kind of little h quantity. So we can write h squared as a small h, or h as a small h times the proper units. So it's megaparsec time meters per second. Or, yeah, I think so, yeah. And this small h is exactly what is a number of order 1, or actually, often, sorry, here it's 100. So you know that the Hubble parameter is approximately on the 70 megaparsec per velocity. And here usually you have h to be a number which is something like 0.72. Okay? And if you use this quantity, of course, you have here the little h when you define the critical density. But then the advantage is that instead of defining omega, I can define omega little h square. Okay? If I define omega little h square, let me look if this board is still clean. No, it's not.
It's kilometers divided by second divided by megaparsec, no?
Yes, sorry. Yeah. Yes. Yes, because this is exactly the Hubble law.
The 100 is also.
Yes, the 100 is still there. Yeah. 100 kilometers per second per megaparsec. Yeah. Yes, so that's why usually we also use the following quantity, omega I h square. And omega I h square, as you see from the definition, takes out the h from the definition of the rho critical. So it is practically nothing else, a rho e over rho critical divided h square. And in this way, this is really a density independent of the value of h you can use. Okay? And this is also a quantity you often see in the cosmology paper, in the fits of the CMB, for example. And in that sense, this one is independent on the value of h you measure, because this is a real density without the dependence on the exact value of little h. Okay. Yes, so okay, so now we are already more or less at the end of this lecture, so let me discuss a last thing, which is the particle horizon, and then we will close for today. We can define a particle horizon, as we saw, for example, assuming that the particle is a relativistic particle. We have exactly the same expression I told you before. The radiation moves along the light cone, so we know exactly how the behavior is. And we can look in some sense at the past light cone, so how far in the past we can look with the light, for example. So we have what is defined as the particle horizon, which is defined as the difference of eta minus the initial eta. And then this is nothing else as the integration from the initial time to time t of, dt divided by a of t. Okay? So this is exactly the expression I had before. Now, I didn't solve the Freedman equation completely, but if you, if you do it, you would find out that if you have the equations I showed you before, the solution usually is, we saw it also that A of t goes like a power law. with a t of alpha. And actually it is also a decelerated expansion, as we saw, as long as you have, for example, a radiation or matter dominating the energy density of the universe. This means that this alpha is actually usually smaller than 1. Okay? Now, if we have a behavior like this, we can immediately put it in this equation and solve the equation for the event horizon. And we obtain the following quantity, which is nothing else as 1 over 1 minus alpha t to the 1 minus alpha. So you see alpha is smaller than 1. This means that 1 minus alpha is positive. This means that the horizon, the particle horizon, is growing with time. So the longer the time passes, the more we can see in the past. This is in the sense of a past light cone. Okay? So as long as we have a behavior of the scale factor, which is power law in time, with an exponent alpha which is less than 1, we will have a past light cone or a horizon which grows with time. So as the time passes, we will see more and more of the past universe. This, of course, is a problem, because it means that if you look at the previous time, you are now observing points which were never in causal contact. Okay? Because since this past light cone is also the, if you want, the causal region, the region which can be in causal contact in the past was smaller than the region it's in causal contact now. Okay? So in that sense, you would start with a small light cone, so this region would be in causal contact, but what we now observe is a much wider region where the things were not in causal contact previously.
But that's a problem only if the things you observe have the same properties, no?
Yes, yes. And this is indeed what we observe, because the CMB is the same in all regions we observe, even if we, in principle, at the time of scattering, of the last scattering of the CMB, these points were not in causal contact with each other. Okay? So this is again, this is another problem which whose solution we will discuss tomorrow. It's again the connection that as long as you have a decelerated universe, you are in trouble also with causality. Because as I said, you see more and more of the universe which should be not have been in causal contact before, and nevertheless, if you observe it, you see that it looks the same. Or at least the temperature, as we saw from the CMB, is the same up to a factor of 10 to the minus 4. Okay? So this is actually the big trouble of cosmology in the case I discussed until here. And this is exactly why we need to go to a phase where the scale factor behaves differently. Now it should be clear that there are many things you can do, but one very simple thing you can do is to have, instead of a decelerated expansion, an accelerated expansion. If you have an accelerated expansion for a period, then the behavior of this integral will change completely. And in particular, if you take an exponential for the scale factor, as we will do tomorrow for inflation, you will observe that you can have, in principle, you can even bring the past horizon to be infinite. Okay, so in this case, the past horizon has always finite size, and the size grows with time. Okay? Instead, as I said, changing the behavior of the scale factor in the past will allow us to solve, in some sense, this problem by going to the solution, a cosmological solution, where the past horizon will go, in principle, even to infinity. Okay, so this one is the other thing I wanted to say today, and tomorrow we will go on in inflation. In principle, also, just let me mention, tomorrow I will see if we get there, but it should be clear that this again is practically the zero order description of the universe. So we have just the perfect fluid, we have just the Friedman-Robertson-Walker metric. But in practice, what we have to do also for describing, for example, the galaxies, the cluster of galaxies, etc., is to go also to the first order in perturbation theory. This means, this we will also discuss tomorrow shortly. This means that when we have the Friedman-Robertson-Walker metric and also the energy momentum tensor, we will add on top of the homogeneous and isotropic variables also fluctuations. The fluctuation will be practically small, so that's why we are able to use perturbation theory, and will deviate from the isotropy and homogeneity. And this will allow us, for example, also to describe the behavior of fluctuation in the density in the universe. Okay, this I will try to get to there at the end of lecture tomorrow. And this is one important cornerstone or structure formation nowadays, the fact that we can use perturbation theory to go beyond the homogeneous and isotropic universe. Okay, I think I will finish here. I am nearly there, and maybe there are also some questions. Yes, there is a question down there.
So experimentally we know that A dot dot is positive, so it is expanded accelerated.
Yes.
Do we know anything about A dot dot dot, so the third derivative? So whether the acceleration is accelerating or decelerating?
Well, in principle, you could try to fit it. I'm not so sure you will ever do it. Also because nowadays we don't really do the fit in that way anymore. Usually you really write down the equation for example, for the dark energy. You decide what type of dark energy you want, and you do the CMB fit with the dark energy type. I mean, in the old days, people were parametrizing. So in the old days, people had a deceleration parameter, Q, which was connected to the second derivative. And then you had the next order, which was exactly the third derivative of the scale factor. And they were trying to do an expansion in this parameter around the present time. But nowadays, people don't do that anymore. So, because of course, the problem is that this expansion, you cannot really use it up to the CMB time, because it's very, very far away. It's a Z of order of 1,000, so you will not be able to have a Taylor expansion up to that value. So this you could still do in principle with the supernova data, which are nearby, and therefore you could try to extract the sector derivative of the scale factor. But to my knowledge, at the moment, people are not really concentrating on that. As I said, we are able now to do a fit. I mean, once you decide what is the type of dark energy you put in, for example, with a different W or with a different, you can have any dependence on the scale factor you want for your dark energy. You can put it in the fit practically and do really the fit of the model. Okay, so the Taylor expansion is a little bit less useful than it used to be. Yeah.
Sorry, I got confused over going from omega to omega h squared. Does it mean that, I mean, like just modulating the h doesn't sound very scientific to me. Does it mean that you're actually like measuring the densities at a certain age, like at a constant age?
No, it just means that you extract the dependence on h.
But like, what does that, like the measurements are actually doing omega h squared, right?
There are different measurements. I mean, CMB, you can do measurement of omega or omega h square. I mean, for example, in many cases, people use omega h square just because there is no dependence on h in the measurement. So the measurement is independent of h.
So does that mean it's a constant Hubble rate, right?
No, the Hubble rate here is 100 if you want. It's the reference Hubble of 100 kilometers per second. Then, of course, if you want to translate it into a real density, you would have to plug in a value of h square. But this is exactly what people don't want to do, because we don't know exactly what is the value of h square. Of course, it doesn't change a lot. I mean, it gets better and better. So perhaps in the future, you would also decide to put a reference h, so little h. But at the moment, it's still so imprecise that people prefer, in some cases, to use this quantity. And this quantity is measured, and it's independent on little h. Yes?
So for the causality argument here, why can you say that these regions were never causally connected in the past?
If I know what is the evolution of the universe, I know exactly what is the particle horizon in the past. And the particle horizon in the past was smaller because the time is growing. So at the early time, so for example at the CMB time, the particle horizon was much smaller than the particle horizon today.
Yeah, but that's for the past light cone. But in the past, if you see the future light cone of the past particles, maybe they all intersect, so they are not really causally.
No, well, the other important point, of course, is that if you go and continue this expansion, you cannot continue forever. There is a zero time if you want. Yeah. And that's exactly the point. Why here you have an initial time, and then, or a zero time if you want to take it as the singularity time, you would start then to expand the universe, and then the horizon will also expand, and actually, if you want, faster than the expansion of the universe.
Enough time in evolution, right, to achieve going back to zero time, so that to cover all the universe until the beginning.
No, this you always go back to the beginning if you want. So this is in some sense, I am assuming I know the evolution of the universe from the initial time to today. And I am assuming it always goes in this way. Of course, I can also do two epochs, one of radiation, one of matter. I can do more complicated thing if I want. But in the case of matter radiation, the behavior is always a power law, so it doesn't change a lot. And the main issue is that the horizon is growing with time. So in the past, the horizon was up. There is no way out. It was smaller. So what I see now correspond to many horizon sizes in the past. And in particular, the problem is the CMB, because we see the CMB to be the same in all directions of the sky. And if you compute it, the horizon size at the time of CMB corresponded to 1 degree in the sky now. So you can count how many horizon sizes it contained in the sky now. And that is exactly the big problem. And you cannot solve it in some sense. As I said, it's a combination of the fact that you have a finite time, so you have an initial time of the singularity, you cannot go further, and also the fact that the expansion of the universe is decelerated. So these two factors conspire in such a way that you have finite size horizon, and the size of the horizon is growing with time. More questions? Okay, then we can break for the coffee. Of course, you are welcome to ask me questions also during the coffee in case. Thank you.